Okay, so hi everyone. I am Guénolé Fiche, and today I will tell you about Motion-DVAE, which is a human motion prior that we use for fast human motion denoising. Before going into the details of our model, I will just present quickly the human pose and shape estimation problem. More specifically, we are interested in the parametric human pose and shape estimation problem, which consists of estimating the parameters of a human body model. So typically, it will be theta for the human pose and beta for the body shape. And with these parameters, we can use a model to generate a 3D mesh of the human body. So to estimate those parameters, there are two main families of methods. The first one is optimization. So we will optimize iteratively the parameters of the body model to match 2D cues, which could be, for instance, 2D key points. And to generate realistic results, in that case, we will use pose or motion priors. So these are models which help to tell if a pose or a motion is realistic or not. And we have regression methods. And in that case, it will be neural networks from the image. They will directly output the parameters of the model. The good thing with regression methods is that they are much faster for inference because we don't need optimization. It will just be a forward pass in a neural network. But the bad thing is they need images with 3D annotations to be trained. And it's not easy to obtain this data. And so what we propose in this work is to do optimization, so with a motion prior, but also to use it in regression settings. We have two main contributions, which are first a human motion prior, which is part of the dynamical variational autoencoder family. So the advantage of this is that contrary to most motion priors, which will only model the transition between consecutive frames, we can have dynamics across multiple frames. And we also introduced an unsupervised learning method to learn how to use this motion prior in regression settings. And if we keep learning on test data, we can, since it's unsupervised, we can do that. And in that case, it will be optimization. And so the main difference between our optimization, our learning, and optimization methods is that we will learn an inference model with neural networks. So we will optimize on the weights of the networks. Instead of optimizing the parameters of a human body. We also model the noise in the observation, which is not always done. And the main advantage is that we can use it in regression mode, so in real time. First, here is the model we use for the motion prior. So we have a sequence of poses, which will be encoded to a latent space with the encoder. And then we have the decoder, which can reconstruct the motion from the initial pose and the sequence of past latent variables. So you can think of Z as a transition from xt minus 1 to xt. And we have then a prior distribution, which gives the distribution of zt depending on the past. So now we want to use this prior we have about motion to denoise observation. So we will we think that the observations are generated with this process. So we have a clean motion, which could have been generated from a latent sequence. And we have some noise which is introduced, and we observe the noisy joints. What we want to do is from these noisy joints recover the real motion, but for that we will recover the latent sequence, and then we can decode it with our model to a real motion. So the inference model is learned by maximizing a lower bound of the log likelihood of the observations, so in an unsupervised way. And once we learn the model, we can do inference in real time with this formula. So in this formula, V is the predicted noise variance. So the higher is V, the less confident we are about the observation. And with this formula, you can see that if the noise is very high, so if we don't trust the observation, we will have a prediction close to X, which is the output of the Motion-DVAE. But if we think that the noise is very low, we will trust more the observations. And so the prediction will be very close to the observation since we trust it. And as I said in the beginning, since the learning is unsupervised, we can also fine-tune the inference model on test data. So it will be a bit like optimization, and it will we will be able to improve the performance this way. So here are the results we obtained. So we compare our method with a motion prior, which is humor, and a post prior, but with a smoothing term for sequences, which is post NDF. So first we can see that we are much faster than other methods, which is normal since we do regression and they do optimization. And we can see that even if we are way faster than other methods, our results are really close to what they get. So V2V is a reconstruction error. So we can see that we reconstruct the motion as well as state of the art for this task, which is humor. And for the acceleration, it's metric which measure how realistic is the motion. So the goal is to be as close as possible to the ground truth joint acceleration. And we can see that humor tends to over-smooth the motion, but it's quite good. Pose NDF is producing motion which are not smooth enough, but it's not surprising since it's a pose prior and not a motion prior. And our method produces realistic motions. So to conclude, we introduced a motion prior based on the dynamical variational autoencoder family for modeling the short-term dependencies in the human motion. And we introduced an unsupervised learning denoising approach to use this motion prior in real time. And so potential improvements would be to include, for example, environmental interactions, such as foot contacts, for example. Or we could improve the noise model or the motion prior.